Right. Thank you.
Okay. So thank you for the opportunity to tell you about this novel data set. I've added authors to the author list as their contributions warranted compared to what was published. So please give them credit for most of the work that's done in here. First, I'll give a 3-minute overview of DART, which was developed by the people listed here and a broader community. And then I'll describe the reanalysis and the resulting data sets. So DART is a flexible suite of software tools to accelerate Earth system research using ensemble filters. We're highly focused on research and the code development needed to support it instead of operational. It's open source with contributions from the community to all facets of the package. And developing an interface to a hindcast model can take as little as a week when model experts work with us. Here are most of the geophysical models interfaced to DART already. Hopefully you can find your favorite. Models in boxes are parts of the community Earth system model used in the reanalysis. DART also includes many low-order models for theoretical development and educational examples. Similarly, there are many here are many of the Earth system observations which can be used in DART already. Several of these represent data sources rather than the platforms that took the measurements. Platforms and boxes are used in the reanalysis. And here's a sampling of algorithms available in DART. I've highlighted a few of the items that may be especially interesting, such as the quantile conserving ensemble filter, which Jeff Anderson developed in the last year, the inverse gamma inflation algorithm from Mohamad Gharamti, and the sampling error correction, which helps correct for the ensemble size limits imposed by resource limits. The code scales well from 1 to at least 100,000 processors, as was needed by this reanalysis. Next are a few examples to illustrate some of the range of research being done with DART. There are a small sampling of the directions in which the use of data assimilation is expanding. Data assimilation for the upper atmosphere is a tricky business since perturbations in the lower atmosphere, which may be caused by data assimilation, can grow exponentially with height. Nick Petitella has figured it out and shown how assimilating Cosmic 2 GPS radio occultation obs improves electron count forecasts. And Ben Galbert's research uses DA to improve the estimates of pollution emissions, which are important inputs to other models and to public policy. DA improves the fit to the NASA DC-8 aircraft carbon monoxide measurements for all synoptic conditions. And finally, for the atmosphere, Craig and Glenn have been pushing toward the goal of global convection permitting DA using the weather research and forecasting model and the model for prediction across scales. The main cost of assimilation in large models like these is usually the model hindcasts. In addition to expanding the use of DA in the atmosphere, it is expanding into other Earth system components, partly because dramatically increasing numbers of observations make it possible to constrain and evaluate the models in meaningful ways. Here's a map of some of the land observing platforms which have become available in the last few years, and the land model variables which they constrain. Data assimilation is often thought of as a solution for initial value problems, but it can also provide boundary conditions at the interface between the atmosphere and the surface components. And here's an example of how some land model variables are in need of constraint. Whoops, that picture is missing. Sorry about that. Anyway, it showed a factor of 10 differences in above ground biomass from a variety of models. Oh, there it is. So the need for data assimilation in many Earth system components is clear, but what about the path to implementing it? We've found that the path involves the use of a modeling system which already handles interactions between a variety of Earth system components, so that the development work can focus on data assimilation. So all of the surface models in CESM are usually forced by the community atmosphere model. But the forcing can come from a reanalysis created ahead of time, shown here, and stored in coupler history files. These files are read by CESM and used in place of an active atmosphere. This is convenient, highly efficient, and provides forcing that represents actual weather events. This is especially useful for surface models, which can be used for assimilations with DART, which are highlighted in the green circles here. A fundamental difference between atmosphere and surface models is that small differences in the initial conditions in the atmosphere grow until the model states appear to be random selections from all the states possible for that date. In the surface models, the opposite is usually happens. Even large differences in initial conditions disappear over time, leading to all model states looking essentially the same. And this is unusable in ensemble data simulation. So here's an illustration from the community land model. The top picture shows what happens to a leaf area index when the initial ensemble has spread, which are the red curves, but the same atmospheric forcing is applied to each. The ensemble collapses with time. The bottom shows the ensemble starting from a single state, green curves, but each member is forced by a different atmosphere from a reanalysis. The ensemble develops and maintains spread, which is crucial for ensemble data simulation. So this is the motivation for one of the largest DART projects, which is the motivation for this talk, the CAM6 plus DART reanalysis. And here's a cartoon of how we handle this problem. On the left, we show an 80-member ensemble of CLM runs forced by a CAM4 reanalysis product. CAM6 will work the same way. These are 80 equally likely CAM model states, which are all constrained by atmospheric observations and which create spread in the CLM ensemble. We then assimilate multiple remotely sensed data products and then adjust the model state to better represent the observations. It's important to note that all of the model states, fluxes, soil carbon, and soil water are influenced by this adjustment, even if there are no observations of them directly. And I'll skip the details. Here's an example of the ensemble forcing, in this case 20 members and the ensemble mean of the downward long wave heat flux. It shows contours of 300 and 400 watts per square meter. This is part of a set of realistic, physically consistent forcing fields derived from CAM model states. The ensemble uncertainty is consistent with the observing network and the model formulation. Larger spread among the contours represents areas where a wider range of forcing must be handled by the model, the surface model. Other motivations for the creation of this reanalysis include providing forcing for offline CAM-based chemistry transport models, or in a nudging framework, evaluate weather prediction capabilities of CAM, which is designed as a climate model, create a very large, order 10 billion, labeled data set of atmospheric observations and ensemble estimates of the observations, which is useful for machine learning, and ensemble plant growth variables, which came at a trivial extra computational cost. So how do we create these reanalysis products? The hindcast model is a 1-degree CAM6 configuration CESM 2.1. It uses an active land model, but the land state is not directly changed by the observations. The sea surface temperatures and ice coverage come from a daily 1/4 degree AVHRR product. The sea ice model plays a similar role to the land model, but for sea ice thickness. The assimilation is set up with 80 members, 4 times per day, and uses the new inverse gamma inflation. And we ran dozens of tuning experiments to find the best combination of assimilation parameters. The land spin-up included about 10 years of assimilation using the existing CAM4 forcing dataset, and then 6 months in reanalysis mode using CAM6. I'll note here that there was no assimilation failures due to the algorithmic choices or shortcomings in the 10 years completed so far. We assimilated several million observations per day, as listed here. Observations which were not assimilated were used in the evaluation of the assimilation, as were the assimilated obs. Here's a sampling of the observation distributions at one assimilation time. Many of the points represent whole profiles of observation. Combined, they give good coverage over the northern hemisphere, but are sparse over the southern high latitudes. This is where the largest ensemble spreads are found. Some observation types change significantly over time. GPS, satellite winds, and aircraft. Think COVID in 2020. The inflation algorithm adapts to this and maintains the appropriate ensemble spread. We evaluated the assimilation status monthly in observation space relative to all observation types. Yes, I looked for problems in over 100,000 pictures. The example on the left summarizes the data from a whole month of radiosonde V wind component observations north of 20 degrees north. It's showing the bias, root mean square error, and numbers of observations available and assimilated. Observations may be ignored for several reasons, including their values being so far from the ensemble mean that we judge them to be incorrect values. But for a difference of 3 standard deviations, this is usually less than 2% of observations. So DART is extracting almost all of the useful information in the observation sets.
Kevin, 1 more minute.
Oh dear. All right, similar thing on the right, but in the time series form. So the resulting data set is 120 terabytes, and it's freely available on NCAR's Research Data Archive. It's organized in the structure of CEM's short-term archiver by component model. It is compressed and packaged into convenient sizes for downloading and using. It is also available uncompressed in NCAR's Glade file system. So a couple of the projects that are using this atmospheric forcing data set is carbon monitoring across the western US. This is an important way that the land influenced the atmosphere on long time scales through the flux of carbon, but the West is a complicated place to do it. And this is work by Shuli Ho, uses a spatial subset of the reanalysis atmospheric forcing in a regional community land model. You can see from the observations and free run that CLM grows way too many leaves in the high latitudes. Assimilating leaf area index brings the CLM model states into better agreement with the observations. A few more projects that are using the reanalysis are CESM's CICE model. It's used for data assimilation, algorithm development, and model evaluation. It's being used in the POP ocean model, and we're developing an interface for the MOM6. The kilocam experiments at KAUST are using very large ensembles to investigate some fundamental data assimilation questions. And another project is enhancing Earth system predictability by diagnosing model error in mode water regions with a variety of contributors from University of Colorado and NCAR. So in summary, DART is a flexible, research-focused community ensemble data assimilation system. It's used for a broad variety of Earth system research projects. The CAM6+DART reanalysis can accelerate research using non-atmospheric Earth system models at lower cost. It provides objectively derived, realistic variability and uncertainty estimates to surface models. You can find extensive resources at this address or email us at the address shown. For a thorough description of the reanalysis, you can see the scientific reports paper at this address. And finally, I'd like to acknowledge the high-performance computing support on NCAR's Cheyenne computer provided by the Computational Information Systems Laboratory and sponsored by the National Science Foundation. Thank you.
Thank you, Kevin. Very, very impressive work. I think that providing large data sets to community to use for machine learning is a very nice opportunity to make use of data. We are aware, for instance, of NVIDIA using ERA5 in ingenious ways to train their neural networks.
Yes.
As for, to provide rapid forecasts. And are you aware of any use for machine learning of the data sets that you have computed?
I started working with a couple of people to use it. We haven't made much progress yet. There have been a lot of competing interests, but there's definitely some interest there, and I think it is a valuable data set for that because of the careful labeling of the data and the extensive number of observations.
Yeah. Well, looking forward to hearing more in future. In the meantime, we have a question from Sergey. Kevin, thank you for your talk. Sergey says, why did you decide to use airs in addition to conventional and GPS observations? I would have thought that a microwave observations like Amsway would be a more obvious choice.
In this case, it was because at the time when we did this reanalysis, we were not able to assimilate the radiances, and so we were using retrievals from airs. In the future, we now have the capability to do radiance assimilation, and so I'm guessing that we would try and include those in future reanalyses.
Okay, thank you, Kevin. There are no more questions, and I will now pass on chairing the session to Laura.